So this problem is asking you to use an alphabet that is much more similar to an alphabet that is actually used in practice. This is meant to be kind of take the ideas that we talked about and you can start to see some of the ways in which they might be applied. So we're going to write a grammar for what is a legal number. Just being able to recognize a number that is typed. So we need to know that it could be signed or unsigned. So that means we should accept negatives. We need some way of finding and utilizing, recognizing that a negative may be part of a number. The value, which is kind of the value of the number, we have two fields, kind of we have the before the decimal and after the decimal. So everything that is in the ones place or greater and everything that is in the tenths place or lesser. And there's a decimal point between them. But it's an optional decimal point, right? Because you can have the number like 364, but you can't have that be the tenths. If it's there without a decimal point, then it's the ones, tens, hundreds, not the tenths, hundreds, thousands, etc. And there's an optional exponent field, which is kind of done in scientific notation, E something.
How many words to write the answer?
Yeah, it's as a grammar. So you should start with an S. Design a grammar set of such numbers. So starting with an S, basically you're gonna say through some rules that generate grammars, can you map this to something that either accepts or rejects some text as a legal number according to these rules or not a number according to these rules.
So you don't want it in the ETS format, you want it in like S equals this.
Yeah, that's perfectly fine. I think that they're probably wanting it in that particular set when they say this, but in general, I can get all the information from that quintuple just from the production list.
Okay.
And I find that it's easier to solve the problem and think of the problem as just a set of productions rather than the entire formal definition. In general, I am just much more interested in, did you solve the problem than did you express it perfectly in notation? Can I get that you understand the problem? I may point out the notation may be a very small deduction, but if the solution is there, the solution is always 95% of what I care about. Okay, some quick announcements before we dive into it. Tomorrow is our big review session. So especially as I mentioned in a small class, please do come prepared with problems. Let me know within a couple hours today if there are any larger scale topics that you'd like me to have examples prepared for so that I can do that. I will still do my best if you come tomorrow with can we get some practice with this kind of problem kinds of question, but I will be coming up with them off the top of my head. And sometimes that leads to worse examples than I could come up with if I have a little bit of time to prepare for it. Especially if you say an example of this where there are this many states or there are this kind of a problem within that has this particular quality to it. I'll need to be able to generate that, a little bit of time for that. Homework is due tonight. You can expect that the next homework will be revealed magically by tonight. That'll be due next Wednesday. Focus on the exam, I think, between now and Friday. Don't worry yourself too much about the assignment. If any of these assignments end up crazy difficult, I have a little bit of flexibility in terms of I can reveal the next one and maybe extend one by a day if the entire class struggles with it. That said, I will be less understanding of that if I haven't seen anybody in office hours. And I think I've seen a grand total of 0 of you in my office hours so far this quarter, and that works as long as you are perfectly understanding everything and it's all happy and rainbows and fairies and confetti. But as soon as it's not, please do come see me. And especially if I see the entire class and you're all struggling with some concept and it just needs a little bit more time to marinate, we'll work with that. And then we do have exam on Friday. That's basically where we are. Questions on upcoming deadlines, what we can be expecting over the next couple of days, next week? Right, I guess we're good to hop right into this. So last time we looked at an algorithm for taking a grammar and converting it into an NFA. No, not any grammar, a regular grammar. And so they either need to be left linear or right linear. So this was a right linear grammar. We started with states representing each one of these non-terminals, and then we added edges in between them, representing transitions that lead you from one non-terminal to the next non-terminal. So we started with an edge between B sub 0 and B sub 1 that consumed an A, and that takes care of this first production. And we needed an edge AB between B sub 1 and B sub 0, since it's not legal to have edge lengths of more than one, we needed to add a state in the middle. So we created a B sub 2. Whenever we have something that terminates the grammar or the string in a grammar, like we do in the very last half of the last production here, this is B. Whenever we see that, that means we need to transition to a final state on consuming that from there. So we had a B sub 1 to a B sub F on a B, and that was the only final state in the NFA. It ended up looking like this. We kind of rushed this toward the end. Did anyone have any questions about this process or about this solution, how the process leads to this solution? Such a quiet class. So different from last time I taught this. All right, so I guess the last thing we want to be able to do is see if we can go the other way. Not quite. So we're going to start with a language, a regular language. And we're going to construct some kind of regular grammar to be able to say, all right, here is a regular expression. AA B star A. And we come up with a right linear grammar for it. Any thoughts about how this might work? Algorithmically, what can you do? And what does a right linear grammar mean in this case? Kind of abstracting from that, what does it mean to produce a right linear grammar that might accept this language? Any thoughts on that? Yeah.
You can define a graphic subset, which is all non-terminals, you just handle it on the right.
Yeah, so we are certainly going to be. So to be right linear, that means that the variable is on the right. So that means we're going to be parsing this from left to right. You start with everything that you know must start the string. So if we wanted to create, we're going to start with kind of an S arrow. Then we need to consume as much of this as we can that we know is consistent. So that's going to break this down into this AA component, because every string in this language must start with an AA. So you can imagine that this S leads to A, and now we need some non-terminal to represent that we don't know what's coming with the rest of the string. So I like to start with capital A. So this just breaks it apart and says every string must start with AA. What comes after that, we don't know quite yet. We'll need some additional rule to define what that's going to be. How in the world are we going to represent this B star in grammar notation? So note that we can't have a capital and a right linear grammar before a terminal. So we'd have to somehow make sure that it comes at the end, but I think you're on the right track here.
B capital.
B capital A, what does this do? Yeah, so you can think of this kind of recursively or self-reference. This allows you to arbitrarily loop this some number of times, where each time you're adding a B to the end of the string. And just like how this B star works in a regular expression, this is an arbitrary number of iterations before we need some way to terminate it. How do we terminate this looking at for a bunch of B's? How can we stop this self-reference process? We don't want an infinite recursive depth. We don't want a stack overflow.
We just do or lowercase a.
Yeah. So we let this capital A choose between two options. This says both, this is optional, we don't have to choose this, and we can choose it an arbitrary number of times. So whenever you see a star closure or a positive closure in a regular expression, you're going to be using some kind of self-reference in your grammar, in some production. So we could generate some things from this by saying S arrow A capital A, and we could choose that this A becomes that A, so we can generate the string AAA. And this tells us one such string that's in the language. Is this string in this language as specified by this regular expression? Yes. B star is 0 or more, so having 0 of them is perfectly acceptable. If we do this once, we end up with the sequence of productions. We go S to AA capital A to, we're gonna replace this A with the first one here. A, B, capital A, and now we could go terminate, end up with A, B, A. Is that in the language? Yes. You can see that we can do this an arbitrary number of times. The number of times that we apply this rule before we apply this rule is just the number of B's that ends up in the string that's in the language. And you can see how this kind of draws out as a tree as well. So maybe you want to visualize this more as a tree. We have the S that we start out with. There's only one path from the root. We're going to kind of add an AA to the string before we are now needing to resolve this A. When we're at this A, we can resolve it in one of two ways. We can either add a B on this edge and end up back at the node A, or we can add an A to this and terminate. And now you can see that since this is self-reference, we now have kind of have a tree version of some iteration of this from the root to a leaf node. Traversing whatever edges that is, ends up with some string that's in the language. This would be a tree of infinite depth. And you could argue that you can kind of stop this process because it's defined by itself via that recursion, but that would be another way to kind of visualize what this grammar is specifying in some data structure or format. Questions about either of those representations or ways of thinking or interpreting the grammar that's there? If anyone else interprets this in any other way, I would love to hear it from you so that I can add it to my repertoire so that I can continue introducing new ways to visualize or think about any of these concepts. These all come from just my own thought experiments on how is this related to things that I've seen before or in conversations from students, past times that I've taught this. They say, well, how similar is it to, and it makes me think of another way to approach this. So if there's any other way that you engage with it or tie it to something that you've learned before, that's an interesting conversation we should have at some point. So perfectly equivalent grammar here, we just said this is a non-terminal. You can easily just move this, since this B only ever becomes that A, that can just be moved up here and it's exactly what we have. Two equivalent grammars, either is more correct. One is a little bit more space efficient in terms of its storage, but we will learn some ways to express grammars later in particular styles so that you don't really have this level of optionality. But for now, absolutely fine. Last questions on anything related to regular grammars and how they relate to every other way that we've had to express our regular language? That's the case, then it is time for our last topic about regular languages. And it's a very important question about regular languages, and there's no easy way around this process, unfortunately. So as we have discussed regular languages so far, we know many ways now how we can show that a language is regular. We can construct a DFA. If we can construct a DFA for a language, then that language is regular. We can construct an NFA. If we can construct an NFA for a particular language, that language is regular. We can construct a regular grammar. If we can construct a left linear or right linear grammar for a language, then that language is regular. We can find a regular expression. If we can find a regular expression for a language, then that language is regular. All of these tools, choose one, and you can answer the question, is this language regular? You don't have to do one or the other, you have plenty of options. However, this doesn't answer the question of how can we show that a language is not regular? So all of these are kind of proof by example. World's easiest kind of proof. You come up with an example and it proves it. Is this language regular? Well, if it's regular, then there must exist a DFA. Here is a DFA. Done. But we can kind of talk about now, coming back to something we talked about a few days ago. What is the structure in general of a regular language? How we're going to need to know this in order to be able to prove that something is not regular. We need to be able to understand that all regular languages have particular properties to them so that we can identify when a language does not have those properties. How in the world are we going to show this? So, don't need you to answer that right now, because I don't think we quite have the information for it. But before we dive into this, we're going to need one quick refresher of something from discrete. Who remembers the pigeonhole principle, or saw the pigeonhole principle in the first place? Long time ago in a galaxy far, far away. An alternate universe, maybe. So the basic idea of the pigeonhole principle is, at its most basic form, we want to put some number of objects into some number of boxes. If we have more objects than we have boxes, then the conclusion is at least one of the boxes has to have multiple objects in it. Does that logically make sense? We have 3 boxes and we have 4 objects. Right, let's make it even smaller. We have 2 boxes and we have 3 objects. Box, box, object, object, object. What are all the ways that we can split these objects amongst boxes?
Put one in one and two in the other.
Yeah, so we could put. Let's say 3 here, 0 here, 2 here, 1 here, 1 here, 2 here, or 0 here and 3 here. So kind of all of our options, 4 options for it. In all 4 of those cases, at least one box has at least 2 objects in it. Is this going to generalize to n boxes and k objects, or n objects and k boxes, as long as n is greater than k? Will it always be the case that at least one box has at least 2 objects? You feel like the answer is yes, not only are you right, but you have the intuition for how to move forward with this idea. If you want to talk about exactly how many objects, then we can take the quotient of n over k, take the ceiling of that, and one box must contain at least the ceiling of n over k objects. So in this case, n was 3, k was 2, the ceiling of 3 halves is 2. Right? You familiar with all this terminology? I probably read this as seal, but I don't want to make seal noises. It's too early in the morning. But about the concept or how it generalizes. Some examples. We have red, green, and blue socks. We're feeling very out there. How many socks do we need to pull out of a dryer at random to guarantee you have a pair? Or you have 1 pair of matching socks, yeah. You know, for sure. Regardless of what happened, you're going to have a pair. It's really dark. So dark you can't see the glowing red, green, or blue socks. It's why you bought them in the first place, so you can see them in the dark. You can't see them in the dark. You're just like, all right, that's a sock. How many of them do you need before you go back to the room in the light? Be like, all right, I know I have a pair for the day. 4. In the worst case, you pull out one that's red, one that's some color you don't have so far, green, one sock or a color you don't have so far, blue. The 4th sock you pull either has to match the red you already have, the green you already have, or the blue you already have. Maybe you were lucky and got it before that. Maybe the first 2 you pulled out were green. But in the worst case, you have to iterate over every object type until you pull 1 more than that, which is why again we have that ceiling of n over k. Because now once we have more objects, then we have types of objects, that ceiling becomes 2. The ceiling of that quotient becomes 2. How many people do we need in a room to ensure that 2 people have the same birth month? 13. In the worst case, the first 12 will have different months, but that 13th person must pair with one of the existing 12. How about at least 5 people sharing the same birth month?
It's not like 5 pairs.
We need 5 people with either January month, February month, March month. We don't know which month it is. We need some number of people in the room to know. And we don't know any of their birthdays, but we know at least 5 of those people will share the same birth month.
49.
49? What makes you say 49?
4 times 12 is 48, plus 1 is 49.
Yeah, in the absolute worst case, the first 48 people in the room can be grouped into 4s. There will be 4 Januaries, 4 Februaries, 4 Marches, 4 Aprils, 4 Junes, all the way to 4 Decembers. That's 48 people. That 5th person has to join one of those groups of, that 49th person has to join one of those groups of 4. creating the group of five. Absolutely right. So this is just kind of a general application of this principle. And it can get significantly more complicated, but we don't need it to for the scope of this class. So look at some pigeonhole principle challenge problems, and you can really get your mind blown. It's actually quite fun. So we're going to take this idea, and how we solve this is going to be one of the applications. Like, we need to understand and know the pigeonhole principle for this process to make sense. So we're going to take an example language, a to the n, b to the n, which just says that we have some number of a's followed by exactly that same number of b's. The question is this regular? If it is regular, you should be able to take one of those ideas, DFA, NFA, grammar, regular expression. Show of hands, who thinks this language is regular? Remember that I spent a lot of time trying to fool you. Can you think of an intuitive DFA for this, an intuitive NFA for this, an intuitive grammar for this? You think so? What's your approach?
S is equal to A S B. With the star. Or it's actually S is equal to A F B for empty set.
That would be great if it were a regular grammar that does not adhere to either the left linear or right linear rules. So yes, we can create a grammar for it, but the grammar requires insertion in the middle, which is not allowed in a linear grammar. Good idea. One intuitive way to think about this is that any DFA will have a finite number of states. So thinking about constructing a DFA, you could start with kind of A to the 0, B to the 0. That tells us that wherever we start needs to be final. Great. So we're going to start at a state Q0 that is final, because we accept the empty string. Now we could say we need to transition on an A, and B will just lead to a trap state. So I'm not really going to draw that. B is just going to go off into the abyss for the moment, just because I don't want to fully flesh out this DFA. But an A would lead to a state Q1 that says we've consumed an A. If we consume a B from here, we would lead to a state Q, I'm just going to call this QF, that says that kind of we've reached that point where we've consumed the same number of A's as B's. Great. And if we consume anything from here, obviously we've seen A, B, we can't go back to A, we can't go to B, so anything from here goes to that trap state. Should probably be drawing some arrows. This should go to Q2 on an A, and now we need to consume two B's. So we're going to go to a Q3 on the first B, and then back to QF on the second B. Now we can consume the third A and go to a Q4. And now we need three B's to get back to that acceptance state. So we need a B to go up in here, we'll call this Q5. We need a B to get back to Q3, but we need one more to go. And then we need another B to go to A sub F. But what if there are four? We're going to need more states. This process actually just continues forever. This becomes an arbitrarily large DFA where we continue this exact pattern all the way to infinity. And there's no other possible really way to construct this DFA that would map to arbitrarily large ends. if there are an infinite number of strings in a language, we need some way to parse in a finite number of states. So that's kind of the intuition as to why this language is not regular. We don't know the size of n, so we can't do much about it, yeah.
So if you can't like generalize a pattern that it wants to repeat, that's how you would know that it's not regular.
Yeah, there is some repeating pattern in it that is what creates that ability to have infinite strings. We're gonna talk about exactly how to formalize that idea, but that's a great intuitive place to start. I think that will help people make more sense, is there must be some allowable repetition somewhere in this. Note that there's no loop in this DFA. You can't get back to any state that you were in. So there's no way to get back to Q0 via some reference here. Once you're at A sub F and you can finalize this, you can't get back there again. So there are an infinite number of strings here. And no matter where you stop this diagram, there will not be an infinite number of paths to a final state. There will always be a finite number of paths to a final state, assuming you stop the number of states somewhere. You need an infinite number of states to have that infinite number of paths to this final state, A sub F. So that's kind of the logic, the intuition for why this doesn't work. So because there are an infinite number of possibilities for n, the size of all the natural numbers, and I'm one of those sticklers that says n is part of the set of natural numbers, sorry, 0 is part of that, then you can use the pigeonhole principle. The pigeonhole principle will tell us that there exists at least one state where multiple values of a to the n map. Does that make sense? So we have a finite number of states. Even without drawing this out, I do this to kind of give you a sense of what this would look like, but now imagine we don't have this. And we're gonna say, for sake of argument, suppose there exists a DFA with a finite number of states. We're just gonna have that DFA, we're gonna represent that with, I don't know, some large circle that says DFA. And it has some number of states, V. There are V states in this DFA. We know all DFAs have a finite number of states, so we're gonna call that number V. Great. Since there are multiple possible paths, there are an infinite number of paths through this DFA that end in a final state, right? Since we know that n can be, there are an infinite number of possible values for n here, there must be at least one state that we pass through as, since there are an infinite number of these and a finite number of these as we get to a final state. Basically, I've drawn out here a DFA where there's no such node, there's no such vertex. How are we doing? Does that make a little bit more sense? Not really. So B is finite, right? We know this is finite. We know n can be, is the set 0, 1, 2, 3, 4, 5, etc., all the way to infinity. Obviously, this isn't a number, this is just an idea. This extends forever. This does not stop. But we need to map all of these values as going through these nodes. For any value in this set, the infinite number of values, there exists some path through these nodes. Which means by the pigeonhole principle, there has to be some state in here that is visited through multiple paths of this. There are maybe 3 and some ridiculously large number. Both pass through some state as we do this. And we're going to use a proof by contradiction to show that no such this can't exist. There can't be a finite number of nodes and an infinite number of possibilities to map to that in such a way such that this DFA construction is possible. So instead of a proof by example, we actually have to use logic. And we'll find that we do this a lot in these kinds of proofs where we say, suppose that this DFA exists. And now we need to proceed by some kind of proof by contradiction that shows that the construction of this DFA is impossible. The logic for that comes when you try to draw it out and you realize that I always need more states. This is a beautiful DFA for a to the n, b to the n, b is less than or equal to 3. That's regular. We just drew a DFA for it. But as soon as we allow an infinite number of values of n, then this becomes impossible. As long as this is finite, that can be finite. If this is infinite, then there needs to be some looping mechanism in the DFA that allows us to visit the same node over and over and over. Each time we go through that cycle, we generate a new string in the language, new string in the language, new string in the language. So it ends up with something like you have a start, you have some finish, you have some middle ground. We get to the middle ground in some way, shape, or form. We do this once. We find through some other path in the DFA, we get from the middle state to the middle state. And then, so we can do this an arbitrary number of times. And then we do this once. And now we can create an infinite number of strings with a finite number of states. And the question is just how many repetitions of this loop do we go through? If we go through 0, then we have kind of the path S to M to F. If we do this loop once, then we have S to M to M to F. If we do this loop twice, S to M to M to M to F, etc. And we can do this an arbitrary number of times, and it will create an infinite number of strings. So DFAs can accept languages that have an infinite number of strings, but all of those DFAs have some structure that looks kind of like this. And note, this is not self-referenced necessarily. There may be some other states that are being visited along this loop. It's just some path through the DFA from some middle state to itself. Note that this could be length 0, and that this could actually be the same starting state. This could be of length 0, and this M could be the final state. We just do this process once, this process once, and this process an arbitrary number of times. That's the basic idea that we're going to be going through, as well as showing how do we represent that? How do we do this in that way? Questions on anything that I've covered to this point? Very abstract. Very theoretical, very out there. So, perfectly okay if this doesn't make any sense whatsoever, or if this is just so out there, like, I don't think this way. I'm hoping that some examples will help. All right. How we proceed with that proof by contradiction from here is we're going to assume that that DFA exists, that will accept a to the n, b to the n, only if n is equal to some value of m. And we're going to say this means that there is some state q that is now kind of the middle of this that we get to once we start at the starting state, consume all the a's, get to that middle state, and then we can move from there to the end via reading some number of b's. That would be true. So yeah, we're basically getting to some place in the middle of the first a's, the first set of a's. So we're gonna read some a's, reach a middle point, read some more a's. This is not the best way to explain this, given the way the diagram that I just drew. Basically, this pump is going to be trying to find the loop. Where does the loop exist? And then trying to proceed by showing the loop has to exist somewhere here. This loop can't exist, therefore the DFA can't exist. Let me give you an example first, because I don't think this is gonna help us. So, some properties. The transition graph has no cycles, then the language is finite and therefore regular. Does that make sense? If there are no loops in the DFA, then there can only be so many ways to get from the starting state to any final state in any graph. If that graph has a cycle with some non-empty label, then the language is infinite. Because of the way that I just showed you before, we can reach that middle point and we can do that loop an arbitrary number of times. So every infinite regular language has a DFA with such a cycle. You can draw that conclusion, basically that if a language has an infinite number of strings and it is regular, then the DFA for that language has that cycle component to it. That we can iterate an arbitrary number of times to generate an arbitrary number of different strings, giving you the infinite language. If there is a cycle, we can of course skip it or repeat it an arbitrary number of times. We're going to relabel everything. The cycle is we're gonna call B for the moment, and the string W sub 1, W sub 2 is in the language. We're gonna tell you what each of these are. W sub 1 is the path to get to the cycle from the start state. W sub 2 is the path from the cycle to the final state. Could be multiple final states, we'll just select one arbitrarily. And then repeating the cycle allows you to show that W sub 1, W sub 2 is in the language. W sub 1, V, W sub 2 is in the language. W sub 1, V, V, W sub 2 is in the language, etc. So now we have some formal way to talk about this idea of getting to that middle state, getting from that middle state back to that middle state via iterating the cycle some number of times, that's V, and then getting from that middle state to a final state, that's W sub 2. So every infinite regular language has this property. You can break it into these components. Now we're going to assume that the DFA has, instead of V, I should have used M from the start, I apologize, has M states. We know that we're going to encounter that cycle by the time we have read M symbols. Why? There's intuition behind this, and it's very important intuition moving forward that everyone needs to have for this to make sense. Sorry. Kind of, yeah, you're gonna be visiting new states. If you ever go back and visit a state that you've already visited, that's a cycle. Exactly. So we have some DFA, let's just start envisioning this, it's like in a line. And we have transitions between these states. M is the number of states in the DFA. If we're imagining some reading, so A, B, A, some string that's in the language, each time we read a letter or a symbol, we're going to be visiting a state that we haven't visited before, as long as we're in this W sub 1 portion. We're getting to the cycle, we haven't gotten there yet. So we will have encountered, we'll have at least started, reached the start of the cycle by the time we read M symbols. I mean, maybe the cycle is right here, at the very end of the DFA. But This allows us 5 symbols to read before we get there. 1, 2, 3, 4, we have to have gotten there by now. To continue this, we have to have visited a state that we haven't visited before. But if the DFA only has M states, by the time we've read that number of states into the string, we found the cycle if it exists. Does that make sense? Super important part of this. Maybe show me some thumbs, so I know the extent to which I should go over this in more detail. How are we doing with this? Doing all right? Very important component, because this becomes how we prove this. Using this principle. If we can identify, this becomes the proof by example, a single string that does not adhere to this property but is in the language can't be regular. So let's go through the actual pumping lemma. I'm going to introduce this and we have 3 minutes, so we'll probably come back to this and it's going to be a while because of review, because of exam. So don't feel like you need to 100% understand this. Immediately, we'll be coming back to it. Learn what you can, sleep on it. We will say, let L be an infinite regular language. Because we know if it's a finite regular language, or if it's a finite language in general, it is regular. So we're going to say, we need an infinite regular language. If it is an infinite regular language, there exists some positive integer m that is the number of states in the associated DFA that you could draw, such that for any string that is in that language, with the length of that string being larger than the number of states in the DFA, which again is possible because it's an infinite regular language, there must be a string longer than the number of states in the DFA. You can break that down into 3 components. We're going to call it X, Y, and Z. So this string that is longer than the number of states in the DFA can be broken down into 3 components. We know the following rules. The length of XY must be less than or equal to M. This tells us by the time we've reached the cycle and iterated the cycle, we must be through 1 cycle in that loop. We have to be through that by the time we reach that mth state. We know that the cycle must exist, so the cycle can't be of length 0. We must consume at least 1 character in the input in order to have gone through that cycle. So that tells us that the length of the cycle is greater than or equal to 1. So again, think of X as getting to the cycle, Y being iterating the cycle, and Z being getting to the final state from the cycle. So getting to the cycle and iterating the cycle has to happen in the first M characters, M being the size of the DFA. The length of the loop has to be at least 1. Such that we now have some number of strings, W sub I, being X, Y to the I, Z, where all W sub I are in L, the language. This means, this is why this is called the pumping lemma. We're going to pump this loop an arbitrary number of times. And the idea is, if we can formulate something that adheres to these rules, that gets pumped such that some W sub I is not in the language, that proves that this infinite language is not regular. So every sufficiently long string in L can be broken down into those 3 parts, right? We have a finite DFA, we can break it down into those 3 components. Getting to the loop, iterating the loop, and getting to a final state. Every string in the language can be broken down that way. Absolutely every one, by the definition of a finite state machine and an infinite language. So this is how we're going to show that a language is not regular. Again, to iterate, we're gonna find a way to state, we're gonna find some example where we break this down, some type into this set. Then we're going to pump the middle section to generate a string that's not in the language. Therefore, we show the language is not regular. We'll get a lot more experience and practice with this at the start of next week, a lot more examples, a lot coming. So I will see you for that. Remember to generate some questions for tomorrow's review section. I won't have a ton of new content prepared. I want to spend the entire class doing review for the exam, so come with anything you'd like extra practice with, confusions. Otherwise, it will be a very awkward class if I'm just staring at you and making dad jokes. I'll see you tomorrow for that. I have office hours starting right now in my office. If anyone has any questions about the homework, the study guide, studying for the exam, etc. See you tomorrow or briefly.